Hello everybody, and welcome to the 10th video in the TypeScript Game Engine tutorial series. So in the last video we completed materials, which gives us the ability to define a texture and define a tint for our on-screen objects, and we moved some stuff around, cleaned some things up. But in this video we need to switch gears a little bit because there are some architectural changes that need to be made to make our engine more flexible and reusable for multiple projects down the road. And so today what we're actually going to do is we're going to do some architectural work in the engine itself and add a couple of things that we need to do to support this. So what I want to do is go over what changes we want to make. The first problem that we have is right now we're drawing a sprite directly to the screen, which might not seem like a problem, but the sprite itself is responsible for some things that maybe it shouldn't be. It's responsible for its position, it's responsible for creating its model uniform matrix, and it really shouldn't be doing those things. That stuff should be offloaded elsewhere. The other problem with this is that right now we're only supporting position, and we don't have any sort of ability to rotate the sprite. We don't have any ability to scale the sprite. We need to add those things in. But what I don't want to do is just add those things here to this class and call it a day, because there's a much more dynamic way to handle this that makes things a lot more flexible than they are currently. Instead of just drawing things directly to a screen, I want to put a architecture in place that allows us to separate concerns a little bit more than we already are. And as you'll see in the future, this will actually make things a lot easier to extend. And so what we need to add is a concept of what we're going to call a SimObject. So a SimObject is an object that exists in the game world, and it has a few properties. It has a unique identifier, it has a name, and that's optional, but naming things, naming our objects in the world can make it easier to identify what they are. It has a transform, and if you recall from some of our discussions about transforms, transforms actually have position, they have rotation, and they have scale. So we need to add support for those things. A SimObject also has children, and the children are SimObjects themselves. So we have this ability to nest SimObjects within other SimObjects, and that gives us the powerful ability to inherit certain properties from its parent. For example, if you have one object that is attached to another object and you rotate the root object, the child object should rotate along with it. And by creating this sort of hierarchy, you're going to see how we actually create those things in the future. And so this gives us a really powerful way to just get that automatically just by adding a child object to a SimObject. We're going to actually go a lot more into detail on that once we actually start creating SimObjects, but I just kind of wanted to briefly discuss that now. So the next thing it will have is a reference to its parent. So the reason that you have a parent is you might have a situation where a child needs to know something about its parent, so we want a reference to that. And finally, the last thing that we're going to have a reference to is the scene. And a scene basically is an object that contains all the SimObjects in the world. So a lot of times you might hear this referred to as a scene graph or something along those lines. That's basically what we're creating here. Okay? And what we're also going to need is we're going to need a container to hold a scene. So what I'm going to call those in this engine is it's going to be called a zone. So a zone might also be called a level. Those two terms are sort of interchangeable. So in this instance, I'm actually going to be calling it a zone. If you're following along, you can call it a level if you prefer. It's really up to you. So a zone is actually going to contain some properties as well. It is also going to contain an ID. It's going to contain a name. It's going to contain a description. And the description is basically like a free text field that will be displayed when maybe we're on a zone selection screen or something of the like. We may not wind up using it, but I want to add support just in case we actually do wind up wanting that in the future. It's a very easy thing to add. As I alluded to earlier, it also is going to hold a scene, which then holds the SimObjects, etc. And so what we're actually going to need is we're going to need something to manage these zones as far as which one is currently loaded, which one's active at any given time, switching zones, things like that. We actually need a class to handle that all for us in a loosely defined way. So we're going to create something also to handle that called the zone manager, funny enough. And it's going to be a lightweight class. It's going to be a very lightweight class, but it will provide us the functionality that we need on the surface. So in this video, we are going to create these things. And it sounds like we're going to be creating a lot, but it's actually not that much once things get broken down a little bit. So the first thing that I actually want to tackle is transform. But in order to actually tackle transform, we need to extend a couple of our classes and add some functionality first. So in our project, if I go to Math and then open up Matrix 4x4, we already have support in here for a translation. And what I actually need now is a new method, and it's going to be a public static, and I'm going to call this rotation X. And this is basically going to provide us rotation Z. This is actually going to provide us a rotation on the Z-axis. And if you recall, the Z-axis is the one that points into the screen. So when we're dealing with 2D sprites, that is the axis that we want to rotate on to actually get a sprite to rotate on the screen. I'm not going to worry about X and Y for right now. I just want to focus on Z. So what we're going to do is it's going to take in one property, and that's going to be angle in radians, and it's going to be a number, and it's going to return a matrix 4x4. So I don't really want to get too much into radians versus degrees here, but radians basically 0 to pi is basically the range of radians, and that represents half a rotation, so 180 degrees. So if you just remember that a full rotation is 2 pi, then you can convert between angle and radians. Angle in degrees and angle in radians. So most math APIs almost exclusively deal in radians because it's much faster under the hood for the computer to understand and perform calculations against. And so that's what we're actually going to use here. And we'll provide some methods in the future to actually convert back and forth between these two. But for now, we just want to go ahead and just create everything in radians. So we're actually going to follow the same pattern that we did for translation. So we want to say let m equals new matrix 4x4. And down here, we want to return m. And what we need to do is we actually need to perform a couple of operations here. So we want the cosine, which I'm just going to call C for brevity, and you'll kind of see in a minute why I'm going to do this. But what we need to do is we need to say math.cosine angle in radians. And again, I'm not going to go into the reasons behind this math. There's lots of videos out there that explain these things, so I'm not going to go into depth here about that. So just take this at face value if you're following along. If you are interested about why some of these things are done, I definitely urge you to look up some videos or do some reading about that. The next thing we need is we need the sine of the angle in radians. So we're just going to say s equals math.sine angle in radians. Okay? And so the next thing that we're going to have to do is we're going to have to assign several of these values in the matrix to actually create our rotation Z matrix. So we want to say m underscore data, and we're going to take the first element and we're going to set that to the cosine. We'll say m underscore data, and we're going to take the second element and assign that to the sine. Assign the sine to that, rather. The next one we're going to modify is going to be the fifth element, and it is going to be assigned negative sign. Whoops, equals negative sign. And the next one we're going to assign after that is going to be the sixth. Whoops, underscore data. And this one is going to be cosine. Okay, so that's pretty much it for the rotation Z. And now there's one more very common operation that we have to do against matrices in game engines, and that is to multiply them together. And that basically just combines them into one matrix. And we are actually completely missing the ability to do that. So what we need is a public static multiply, and we want to take we'll call it A for the first matrix, and it's going to be a type matrix 4x4, and B for the second matrix 4x4, and it's going to return a matrix 4x4. And similar to the rotation and the other functions here, we're actually just going to follow the same pattern of creating M and returning M. For this particular method, I'm actually going to paste in some code that I've done before for another project, because this method is really long and I don't necessarily want to go into all the details of it. So I'm actually going to just copy this, and if you read through this code you can kind of figure out what it's doing, but I just want to paste that in there because I don't really want to sit here and type this out, because that would take a while to actually do. So again, if you want to read up on matrix multiplication, I urge you to go ahead and do that, but for now we're just going to use this code that I've already done previously. There's one more thing that we need to add to our matrix class, and that is the ability to create a scale matrix. And so a scale matrix is actually pretty straightforward. It's actually one of the most straightforward ones here. It's pretty much it's as basic as translation, actually. So I'm going to create a public static, and we're going to call this scale. And I'm going to take in a parameter called scale, and it's going to be a vector 3. Whoops, vector 3. There we go. And it's going to return a matrix 4x4. Okay? And since I'm going to follow this pattern again, I'm just going to copy and paste this just for brevity. Okay? And we actually only need to set 3 of the elements in this matrix. So we're going to say m underscore data, and it's going to be the element 0, and that's going to be set to scale.x. Next one's going to be m underscore data, and it's going to be the element 5. We're going to set that to scale.y. And finally, m underscore data, and this one is going to be index 10, and it's going to be set to scale.z. And that's it. Creating a scale matrix is that easy. So really the most complicated one here is rotation, and rotation is actually always going to be the most complicated. So that's the reason I'm not really going into that too much. But this should be everything that we need as far as our matrix class modifications go. So the next thing is we want to actually create a class to handle all of our transform logic for us, so that we can just use a transform instead of having to declare a position, rotation, and scale for everything that needs those values. So what I'm going to do is under math, I'm going to create a new TypeScript file, and I'm going to call it transform. And we're just going to set this up, namespace TSE, export class transform. Okay. We're going to need a couple of public variables. So we want a public, we're going to call this position. It's going to be a vector3. And we're going to default that to vector3. Oh, okay. I actually forgot. I need to add one convenience method to our vector3 class. So if I open up vector3, I actually need to add in a static method. So public static, and it's actually going to be a public getter, and it's going to be called 0. And what this is going to do is it's actually going to return a new vector3 with all of its points set to 0, which, if you recall, is the actual default. So all we have to do here is return new vector3. Now, what this provides us is a nice shortcut in our code to be able to say vector3.0 to get a new vector that's filled with zeros. And yes, we could say vector3 or a new vector3 in our code. This is just sort of a shortcut way to do that. But the reason I'm doing this is because we actually need a second shortcut that I will use here in a moment. And this one's going to be called 1. And it's going to return type vector3. And we're going to again return a new vector3, but this time we're going to pass 1 for x, y, and z. And so now we can say vector3.1 or vector3.0 in order to create a new vector with those values. So as I started to type here, we're going to default our position to vector3.0. And just to clarify on something, we wouldn't want to create this vector once statically and then return it, because then if you ever modified what was held in this vector, it would actually screw things up across the board. So whenever we call this static getter, we're actually wanting to create a new vector3 so that we don't have the same reference being used all over the place. So I just wanted to point that out. Okay, so the next thing we need is we need a public, and we're going to call this rotation, and this is going to be a vector3 as well, and it's also going to default to vector3.0. And finally, we need a scale, and it is also of type vector3. It is going to default to vector3.1. And the reason for that is if you have something that's set to a scale of 0, it's not going to appear on the screen, because ultimately when you multiply by 0, you get 0. So the default for scale is always 1s in all axes. And so that is the reason that we need this vector3.1, is so that we have something to default our scale to. Okay, so we also want a couple of utility methods in here. So we want a public, and we're going to call this copy from, and it's going to take in a transform of type transform, and it's going to have a return type of void. And before I can fill this one out, I actually need to go back to vector3 and add a method that's called the same thing. So we need to add a public, not static, public copy from, and it's going to take in a vector3, and we'll call that vector, and it's going to have a return type of void. And what this is going to do is it's going to say this dot x equals vector dot x underscore x. And I want to use the underscore version so that we don't have to go through the getter logic to actually do this. It'll make it a lot faster that way. And so I'm just going to change this to y, change this to z. So it gives us a nice way to copy over the values from one vector to another. And so as you may have guessed in the transform, what we're going to do is we're going to say this dot position dot copy from transform dot position. And then I'm just going to copy that line and paste it 2 more times, and we're replace position with rotation, and replace position with scale. So it's a nice, quick way to create a copy, or to copy values from this transform to another transform, which we are going to need to do at some point. Another thing that we're going to need to do is we're going to need to get a transformation matrix from this transform. So we need another public method, and we're going to call this getTransformation matrix. And it's going to return a matrix 4x4. And so what we're going to do is we're going to say let translation equal matrix 4x4 dot translation, and we're going to pass it this dot position. And then we're going to say let rotation equals matrix 4x4 rotation z, and we're going to pass it this dot rotation dot z. We're not going to be concerned with the other two axes for right now. We'll add that functionality later when we get ready to switch to a 3D context, which we're not going to do in this particular tutorial series. So I'm just going to leave that as is for now. But what I am going to do is actually put a to-do comment in here. Add X and Y for 3D. Okay, and the next is going to be, we're going to say let scale equals matrix 4x4 dot scale. We're going to pass this dot scale. Okay, and finally what we're going to do is we're going to return a multiplication of those three things. And order here does actually matter in terms of what order you actually multiply these things in. So we want to multiply translation times rotation times scale. So TRS, that's the order that we want to actually multiply these things. So in order to do this, we're going to say return, and we're going to say matrix 4x4 dot multiply, and then we're going to say matrix 4x4 dot multiply again, because we're actually going to pass the result of another multiplication that's going to happen. And so we want to pass in translation, and then we want to pass in rotation. So we're going to say take translation and multiply it by rotation, and then return that as the first, pass that in as the first property to this outer multiply. And as the second parameter of this outer multiplication, we're going to pass scale. Okay? And so that will give us essentially our local transformation for any of our objects that we're going to use. So for right now, this really should be all we need to do for the transform class. So let's go ahead and just save that off. And so now let's just refer back to our list. So we have our transform, which is our position, rotation, scale. And so the next thing that we're going to do is we're actually going to create this SimObject. And in order to do that, what I'm actually going to do is create a new folder under core. And I'm going to call this, let's call this world, because this will represent objects that are in the world, or things that are in the world. And we're going to add a new TypeScript file, and we're going to call this SimObject. This is going to be similar to before. We're going to have namespace TSE. And we want to export class SimObject. And if we look back here, we need ID, name, transform, children, parent, and scene. So what we want to do is we want to say, let's create a private underscore ID, and that'll be of type number. We can create a public name of type string. Let's also create, let's make this a private underscore children, and that's going to be a array of sim objects. And let's also set that to an empty array. Oops, children. And the reason that we want that private is because we actually don't want to be able to edit that array directly. And I'll go into some of the reasons for that here in a moment. What are some of the other things that we need? So we need a transform, and we need parent and scene. Okay, so we'll add parent, which is a SimObject. We're going to add private scene, but we don't have anything for scene yet, so I'm actually going to comment that out for right now. And the last thing is going to be public transform, and that's going to be a type transform. And we'll go ahead and set that to a new transform, just so that we always have a default there. Okay, and we also need a public constructor, and that's going to take in a few properties. It's going to take in an ID, which is the number, and that's going to be the unique identifier that we're going to use so that we can always reference things by ID from anywhere. The next thing it's going to take in is name, type string. Okay, I believe that's actually all that we need to take in. So we're going to say this.id equals ID. We're going to say this.name equals name. And that should do it for our constructor. We're actually going to need a couple more properties, a couple more private properties. Let's say private, and let's call this, we need a local matrix, matrix 4x4. And let's go ahead and set that to matrix 4x4.identity. And what this represents is the local transformation matrix. So we can always pull it from transform, but we basically want to keep a copy of that here. We're actually going to need that later when we start to talk about parenting. And the next thing we're going to need is a world matrix. And it's also type matrix 4x4. And we're going to do the same thing, set that to matrix 4x4 identity. And so this will be the resulting world transformation matrix. So basically the transformation matrix will take into account its parent. So when you have a scene that looks like this, for instance, you have your scene, and then you have SimObject, and then its children might have SimObject 1, SimObject 2, SimObject 3, etc. And then maybe 2 also has another SimObject A, whatever. So the world transform of this object is actually going to take into account the transform of this object and the transform of this object, so that it moves relatively to these other things. So we need to actually track those things separately. So that's the reason that we have both a world and a local matrix. Cool. So let's go ahead and create a couple of quick getters for some of these things. So we need to public getter for the ID, returns a number, and return this.id. And we need a public, public get for the parent, because we actually don't want to set it this way. And again, I'll come back to this, but let's just return type SimObject, return this.parent. Okay, and we're also going to need a reference to the, or an accessor, sorry, to the world matrix. Again, this should be read-only, so this is going to return matrix 4x4, return this dot underscore world matrix. Okay, now comes the part where we deal with the child objects. So actually, before I move on to that, we're going to need a couple more things. So we're going to need a few methods. We're going to need public update, and it's going to be taken at delta time. We'll just call that time, which is a number, and this is going to return type void. And we also need a public render. Doesn't take in, it doesn't take in anything for right now. That's actually definitely going to change in the future, but for right now, we won't take in anything there, and it will have a return type of void. Now that we have this, we need some way to be able to add and remove children, because we haven't exposed this. And the reason for that is because we actually need to set a couple of things when we do that. So let's create a public, and we'll say add child, and call the parameter child of type SimObject, return type of void. And what we want to do is we want to set child.parent underscore parent equal to this. So this is one of the reasons why parent is not settable from outside this class, is because the only way that this should ever be set is through add child and in a moment remove child. So we set that here, and then we say this.children.push child. And that should be all there is to that. The next thing that we need to do is we need to say remove child. So let's create a public remove child, and we'll take in a child object again, and this will have a return type of void, and we'll say child.parent equals undefined, because we want to unset that. And then, in fact, let's actually wrap this in a conditional though, because we want to make sure that the child that we're trying to remove is actually a child of this object. So what we want to do is say this.children.index of, and then we'll say child is not equal to -1. So in other words, only if we find the child in this game object do we want to do this. So we'll unset the parent, and then we'll say, let's actually modify this a bit. Save off the index here. We'll say let index equal this children index of, and then we'll say if the index is not equal to -1, meaning it was found. Then we can say this.children.splice, which is JavaScript's way of removing an entry. And we want to say at the start, we want to say index, because that's the position that it was found at. And then we want to delete 1. And that will remove it from the children array. And let's see. We actually need one more method that we're not going to use right away, but it's going to be called public load, return type of void. So let's see. I believe that is actually all the public methods that are needed for right now. You know what? Let's modify render. Let's go ahead and add the parameters that I was thinking of adding before. So we need to know what shader's rendering it, and that will be important in a little bit, but we can't really do without that information right now. So the next thing that we need to do is we need to add the ability to find an object within this object by name. And that will make it so that we can actually search the entire scene, all the objects in the scene and all the children of the objects in the scene, to try and find an object by name. So we're going to add a recursive method here, and we're going to call this get object by name, and it's going to take in a parameter called name type string, and it's going to return a sim object. And first we're going to check and see if this object meets the criteria. So we say if this name equals name, return this. right? So if the object that we're searching for is this object, just return this object. Otherwise, we need to actually search through our children recursively. So what we're going to say is we're going to create a for loop, and we're going to say let child of this dot children, and we're going to say we're actually going to store the results. So let result equals, and then we're going to say child dot get object by name. This is where the recursive bit comes in. So we're basically going to search this child and its children and so on for a object with the name provided, and store that result, and then say if result is not equal to undefined, that means that we found something. And so we're going to return the result in that case, and that will break out of the recursive function. And then all the way down here at the bottom, we're going to return undefined if we found nothing. And so basically from any object, we are going to be able to search all the way down the tree for an object by name. And so you'll see where the power of this comes in a little bit later, but I wanted to go ahead and get that in there now. So what we need to do next is, since we have a load, we actually need to add another property. I'm going to call this private is loaded, and it's a type boolean, and we're going to default it to false. So this is just an easy way for us to tell if this object has been loaded or not. And I'm going to go ahead and create an accessor to it. Public get is loaded. Return type boolean. Return this dot is loaded. Okay, so now in load, we are actually going to say this dot is loaded equals true. So not doing a whole lot of fanciness here, but you'll eventually see where this comes into play in a little bit. We want to loop through the children in a recursive manner again and make sure that they're loaded too. So we'll say for let c of this dot children c dot load. Okay, and that's all we need to do for that. Next, we want to do something very similar with our update logic. So we want to say for let c of this dot children c dot update and pass time down. Okay, so now we recursively update all of our children. And I'm actually going to, time, not tame. I'm actually going to copy this logic down to render and just change that to render, change this to shader. And so now what we get is we automatically, whenever we call update on this object, all of its children get updated. Whenever we call render on this object, all of its children get rendered. So this is going to be a very powerful way for us to handle updating and rendering across the system. The next thing that we need to do is we actually need to create a scene that holds all of this information, that holds these SimObjects. So under world, I'm going to create a new TypeScript class, TypeScript file rather. Just going to call this scene, as you might have guessed, namespace TSE, export class scene. And the scene actually isn't going to be too fancy at all. It's actually just going to expose a few properties. So all we really need for the scene is a really just a root object. So this is one SimObject that is going to be present in the scene, and so all other objects that are added to the scene will be added ultimately to this root object. So when we render the scene, we'll actually be calling render against the root, and then it trickles all the way down using our recursive methods. And actually, for right now, that's all we're going to add as far as private properties go. So let's go ahead and create a constructor. And we want to say this.root equals new SimObject. And its ID, we actually want to pass 0. And its name, let's go ahead and call it __root in caps __. Chances are nobody's actually going to name another object that, so it'll make it easily identify that that's the root object. Alright, so we need to add a get accessor to the root, so let's just do that real quick. We'll call it root. Turn type SimObject. Turn this.root. Let's go ahead and expose an isLoaded. So we want to say get isLoaded, and that returns a Boolean. And we're going to return this root isLoaded. And so if every object in the scene is loaded, then the scene is loaded, is considered loaded. Pretty straightforward. Okay, so next we're going to say add object. So it's going to be a public method called add object, and we want to just take in an object, SimObject, turn type void, and what that's going to do under the hood is going to say this.root.addChild object. And that's it. So now we can just say scene.addObject, and we can just add an object automatically that way, and it adds it to the root of the scene. If you wanted to add it to a specific node in the scene, you would just need to get that node from the scene. And to do that, we create a public get object by name, which matches what we have in the game object. The sim object. And we'll take in a parameter called name, type string, and return a sim object. And that's going to return this.root.getObjectByName, pass name. So this is where the power of those recursive methods comes in, is now we can just search our entire scene for an object by name, and we'll get the reference to it that way. You don't want to necessarily do this too much, because it is going to be searching every object in the scene until it actually finds one. So that can be expensive if you have a lot of objects in the scene and it happens to be towards the end of the scene. But it's a nice, quick, convenient way to get an object on occasion if you need to do that. So the next couple things that we need a public load method, and it's going to be void, and as you may have guessed, we're just going to call this.root.load, and also need an update time number void this.root.update time, and render just takes shader this.root render shader. So now we don't have to actually call individual objects to render them out. We can just say, hey, scene, render, and it just handles it. So now that we have our scene, we actually need to go back to our SimObject and add our missing scene property. So just add that there, uncomment that, and in our add child, we want to set the scene to the scene of the parent. So we want to say, let's actually not set it there. Let's create a new method in here, new protected method. And we're going to call this onAdded. And this is basically going to be called whenever an object is added to this object. And it's going to take in a variable called scene of type scene. And the reason we're making this protected is because if we have any classes that override SimObject, we want to be those to be able to take advantage of this functionality as well. What this is going to do under the hood is just going to say this.scene equals scene. Okay, and then in add child, we're going to say this dot. Actually, I'm going to say child dot on added, and we're going to pass it this dot scene. Okay, so one more thing that we need to do is back in our scene, we need to set somehow the root game object's scene to be this scene whenever we so that way whenever we add an object through this, we automatically get this scene reference added as well. So to do that, what I'm actually going to do is modify the constructor to SimObject, and it's going to take in another property which is optional, and it's going to be a type scene. And so now we can say this dot scene equals scene. And so 90% of the time we're not actually going to wind up using this, but if we explicitly wanted to add something to a specific scene, we could do it that way. But the reason that we need that is when we create this dot root, we pass this to it. So that way we automatically have the scene added to the root game object, which means that any children that get added to the scene will get that scene added as well. So looking back at our list, we have our SimObject all created out with all of its properties, and we have our scene created with all of its properties. So this is actually enough to start moving some things around. So I think what I'm going to do is I'm actually going to stop this video here, and we're going to tackle this section in the next video because I don't want this one to run too long. So stay tuned for the next section where we're going to add zones and get that set up to actually contain a scene, and then we'll add our zone manager to be able to switch from one scene to another and hook that into our rendering system and so forth. So thank you guys very much for watching. I hope you enjoyed, I hope you learned, and I will see you guys next time.